I present you a magnetohydrodynamic pump, which uses current and magnetic fields to propel liquid metal without using any moving parts. Using this technology, scientists and engineers move molten metals and salts both in scientific and industrial applications. For example, electromagnetic pumps are used to move sodium both in existing and future nuclear reactors. I have built two simple demonstrations which show how MHD conduction pump works and how a Lorentz force in general causes movement in liquid metals. We start with pouring in 20 kg of liquid GaInSn. For experiment to work, we need an electrically conductive fluid, and liquid metal happens to fit the description. Under the box there's a permanent magnet which creates around 150 millitesless of vertical magnetic field in the container. GaInSn, when exposed to air, forms the dirty oxide layer, which we often remove to get the reflective surface. Last key element is a high power current supply, which together with the copper electrodes provide a direct current perpendicularly to magnetic field, creating a setup what we among scientists call MHD conduction pump. We begin the demonstration series with a relatively low current of 100 amperes. Passing the current immediately starts pumping the metal. In this setup, we simply put the pump in a rectangular box. Usually, it would be a part of an enclosed circuit, but in this demonstration, we want to visualize the flow. With the increase of current, forces also rise proportionally. We see that the metal is propelled in the middle of the channel and it recirculates through sides back, forming two eddies. In this setup, we can supply up to 1000 amperes of current through the metal, but using only 0.9 volts. This is possible because cross-section of our conductor is massive, thus having little electrical resistance. We can vary position of electrodes, thus creating different recirculating flows. For example, here, putting these electrodes diagonally creates one large eddy in the container. In this case, the current is flowing across the container, as shown in the sketch. I also changed the position of electrodes in real time. Doing so, you can even see pretty flow transitions, like this one, which briefly creates 4 liquid metal eddies in the acrylic box. Alternatively, if we keep electrodes where they are and change the magnetic field, it's possible to change the flow type. Here I remove magnet from the bottom and slowly reintroduce it from the top. Current meanwhile is constant, but with no magnetic field, the flow stops. This demonstration highlights the fact that we need both magnetic field and current density to cause meaningful forces. My most radical attempt was putting an insulated magnet inside of the metal. Doing that, I was caught off guard by the drift of the magnet. This nuisance was solved by a stick. However, despite radically changing current and magnetic field distribution, this approach of putting magnet in the metal did not create anything spectacular. Another setup worth mentioning is to have a same vertical magnetic field and choose a circular electrode. That completely changes current distribution. Here it flows radially from center to outer ring, but still makes right angles to magnetic field. This creates tangential force, thus creating a vortex-like flow. This setup highlights existence of axially symmetrical problems with current injection. I've also added our paper in the description which looks at a similar problem of weld pool modeling. Just as before, increasing the current creates larger forces resulting in a more intense flow. The upper limit of current we could pass here was 100 amperes, until we started losing electrical contact, thus self-limiting the flow intensity. Here we cannot rise the current more, since interruptions are not good for the power supply, and during the arc discharge, metal is vaporized, potentially creating unfriendly chemical compounds. In the next video, I'll explain more in detail the physics and mathematics of Lorentz force in continuous media in all the experiments I showed you here. There you'll also see some of the numerical calculations for current density, magnetic field, and force density. Thanks for watching, and don't forget to like the video for more magnetohydrodynamics content.